Swayam Prabha. Digital India. Educated India.
So in the last lecture what we had covered was a little bit about microphones. We had gone through a range of microphones, classified them. We also went into details of two specific types of microphones, pressure mics and pressure gradient mics, and explained how each of these mics works and under what circumstances each of these two different categories of mics are appropriate for usage. We'll continue on that journey today. What essentially we'll cover today is explore a couple of other instruments which are similar to mics, but they help us measure vibrations or accelerations, even though they operate on a very similar principle as that for microphones. Following that, what we will do is we will do some numerical calculations and manipulations on a term called microphone sensitivity, and also on the decibel scales. How do you add up decibels, subtract decibels, and so on and so forth. So that is what we will cover today. Essentially what we are doing is, we started with physical acoustics. Now what we are doing is trying to figure out the electroacoustics part. We covered loudspeakers. Now we are covering microphones, which help us measure sound levels. And then maybe in later part of the course, what we will go for is controlling sound, dampening it or reducing the sound levels. And that relates to not only physical acoustics, but also a little bit about psychoacoustics. So what I'm going to start with is an instrument called seismometer. And like a microphone, seismometer. So very much like a microphone, what it has is, it has a moving coil. We do not call voice coil in this case because it does not sense sound, but it senses vibrations. And this coil is embedded in a magnet structure. So as the coil moves up and down, current gets induced, and we measure voltage across the coil, and we sense vibrations. So the way it is that, let's consider that this is a structure, and it is rigidly connected to ground, and let's say the vibrations in the ground are Y. The construction of seismometer is something like this. So I have a motor structure, and within this motor structure I have a voice coil. Not voice coil, just a electrical coil. This coil is connected to a mass, let's call it M. And the mass is connected to the outside frame by a spring of stiffness S, and we could also have some dampening, and let's call this damping coefficient is R, or resistance. So what you have here is that through this motor structure, magnetic flux cuts I mean, this is how magnetic flux moves. And it cuts the conductor, which is wound around a bobbin called the, so that is the coil, and that induces motion in the coil. And because of vibrations, the coil moves relative to this magnet, and that induces voltage. And we connect it to an external voltmeter and sense the vibrations. The mass can have its own motion, and let's call it x. And x may not be necessarily same as y because of these stiffness elements, which may not be infinite in number. So if s is infinity, then x equals y. Otherwise, x may not be same as y. Let's define a term neta equals x minus y. It could be of this form, e j omega t times a constant neta o. The question is that if I can measure this term through voltage, because that's what the voltage will get translated, I mean, is a reflection of this x minus y. How can I figure out the value of y? I'm interested in how much the structure is moving. So that's what we'll do. From equation of motion, we know that mx double dot, mass times acceleration, equals minus s times the relative displacement or the compression or tension in the spring minus the viscous force. And from 1 we can write x equals eta plus y. So if I put that back into 2, what I get is m neta double dot plus m y double dot equals minus s neta minus r neta dot. I can rearrange this entire equation and write it as my double dot equals mass times neta double dot plus the damping force plus the force due to the spring. And if I have y of the form y equals y naught e j omega t, then what I get is basically my left side becomes m omega square y naught e j omega t equals this entire term. Right. Now in reality, y does not have to have this exponential form. It can be any complex signal which could have any shape. But we know from Fourier transformation principles that we can break up any complicated signal into a Fourier series. So if I have a solution for this, I can use that in understanding to decompose any incoming excitation into a sum of different waveforms. This is my equation. I label it 3. And if I do a little bit of math on this, I am skipping a few specific mathematical steps, operations. What I get is relative velocity neta naught equals m omega square y naught e j omega t minus alpha over m omega minus s over plus r square, and this entire thing is under the square root sign. And what I have done is here is I have introduced a new term alpha, and basically alpha is tan inverse the magnitude, which is this term, is this expression neta naught equals m omega y naught times m omega minus omega square plus r square. I call this 4. So now I introduce another term, and eta equals r over r critical. R critical is my critical damping frequency, and this is essentially twice of underscore mass times stiffness. So if I plug this into 4, what I get is eta naught equals y naught times omega over omega naught square divided by omega over omega naught square minus 1 plus 2 eta times omega over omega naught whole square. So I understand that I have skipped a few mathematical operations.
Sir, what is place R critical?
So if you remember, in one of the very early lectures we had said that there is a critical damping that is associated with this R critical.
And the omega naught is the
Omega naught is essentially stiffness over mass, whole thing under square root. Okay. So what I have here is an expression of neta and y naught in terms of omega, right? And this factor which relates to damping. So what I'll do is I'll now plot this relation. So what this is telling me is how the magnitude of neta and y naught are related, right? So what I'll do is I'll construct some plots. On my x-axis I have this parameter omega over omega naught, and on my y-axis I have neta naught over y naught, and this is a linear scale. So all the curves for, and what I'll do is I'll construct different curves for different values of eta, this term. So for all these, all the curves start from origin, because when y naught is 0, then eta naught is 0 identically. So let's say this is 1. So these are very standard curves, and what the curves look like is this is eta equals 0, and then it again comes down and has some sort of an asymptotic relationship as omega goes to infinity. So this is still 0. So it blows up at omega over omega naught equals 1. I'll draw two more curves. This is eta equals 1, and I'll draw third curve. It goes up and then starts becoming flat, something like this. And again, this is eta equals 0.5. So for value of eta equals 0.78, it will lie somewhere between green and blue curves, right? So what we see here is that eta, if it is in this range, 0.7 to 0.5, essentially we get a fairly flat frequency response once my omega divided by omega naught is above somewhere 2, and omega over omega naught I get a flat frequency response. So this seismometer will have essentially have a flat frequency response for, if I set the damping coefficient, this value of R in such a way that eta equals 0.7 in that range, and if my omega over omega naught exceeds 1 or actually 2, then my response curve will be fairly flat. So that is the magnitude part. What else are we missing? There could be a phase also. There's a phase relationship, and ideally we would like that whatever excitation is coming in, which is y, it is in phase with whatever we are measuring, which is neta, right? Otherwise, for each particular frequency, we'll have to fix a specific phase correction factor. So ideally we would like to have constant, zero phase difference for all frequencies, or if we don't have zero phase difference, then as a second best solution, it should be constant, right? So what we will now do is we will plot the phase value. Let's say tan beta equals minus 1 over tan alpha. But even before that, this relation, what we see is the phase difference between neta dot and y is alpha, right? So the so between neta dot and y, I have phase difference of alpha. And if I integrate neta dot, I get neta, and then between neta and y, my phase difference is alpha plus pi over 2, right? Given that we define this term, beta equals phase difference between y and neta. So beta equals tan inverse R over S divided by omega minus m, times omega. And this is tan inverse 2 eta omega over omega naught divided by 1 minus omega over omega naught, the entire thing squared. So now what I'll do is I'll plot beta as I vary eta for different values of omega. So on my horizontal axis I have normalized frequency, and on my vertical axis I have phase difference between the motion of the rigid mass and the motion of the structure. Pi over 2, 0, 1, 2, 3, 4. So when this thing is 0, eta, then my beta is basically pi. And then for other values, I have an inflection point, or so this is eta equals 0.5, and this is eta equals 1, and somewhere in the middle eta equals 0.7. So again, by looking at this particular curve for magnitude, we have said that what this curve shows is that I can reliably measure the relationship between eta and y is pretty much a fixed constant for eta equals 0.5, 0.6, 0.7 in that range, and also for omegas which exceed omega naught by a factor of 2. What this curve shows is that, let's say if I pick up eta so anywhere between 0.5 and 0.7, I have a fixed phase difference which is a little less than pi, and if I keep my omega divided by omega naught above a ratio of 2, then that fixed constant is same for all frequencies. Based on this, I know how to calculate the phase difference between source excitation and whatever the instrument is measuring, and also I know how to translate that voltage into the actual displacement. One thing in this picture what I have not shown is how is eta connected to voltage. That relationship has not been explicitly defined. But in our earlier classes, we had shown that this BL term connects the velocity with the voltage. So we can use similar transformation relationships and figure out, develop the entire electromechanical model. What here we have talked about is just the mechanical portion of it. So that was a seismometer. What we'll talk about is now how the same device could be also used as an accelerometer, and it helps us measure accelerations. Neta naught equals y naught second derivative, and I'll define what that term means, divided by omega square over omega square this entire thing is squared plus 2 eta omega over omega naught, and this entire thing is also squared. What y naught is, double dot is acceleration amplitude. Okay, so it's the amplitude but of acceleration. So I can rearrange this equation in such a way that I get a term omega naught square divided by y naught double dot, and this I call q, and a lot of people call this q as mobility. And the the radical sign, the terms are same, so I don't have to repeat. So now if I plot this equation, q on the vertical axis versus normalized frequency, and this is what I get. So what I'm plotting here is q. On the horizontal axis I have normalized frequency omega over omega naught. So that's my q equals 1. Zero 0.5, 1.5, and my normalized angular frequency is here 0.5, 1, 1.5, and so on and so forth. So in this case, all the curves start from when omega is 0, q is identically 1. So all curves start from here.
So we are interested in finding acceleration. So we must plot 1 over q instead of q.
Yeah, you can do that. But what you will measure is the neta naught, right, through the voltmeter, and that you have to convert it into acceleration. So what we are trying to do here is essentially see again where is the response curve flat. That's all we are trying to do. So this is one curve, then for eta equals 1, something like this, and then it becomes flatter 0.7, and then it becomes even more flat at and then if I reduce my eta further, then it becomes something like this. So what this shows is essentially that the operating range for the accelerometer accelerometer is a very narrow band. It's a narrow band. So if you want to make your accelerometer measure large, very high frequencies, you have to increase the stiffness very significantly. Omega naught has to go up, right? That is what a lot of accelerometers do. They try to increase the stiffness as high as possible. And they do it by using solids like piezoelectric crystals. They act as stiffness members also. So they have stiffness and they also generate voltage. They do both the function. They act as stiffness members and they also generate voltage across themselves.
So after 1.5 they also seem to be flatter.
So this is a better looking curve, should be something like this. Something like that. Does not become very asymptotic. Okay, but it is still flatter here in this range. Now the problem with this, so the challenge is that if I have to measure at 100,000 hertz the acceleration, then I have to maybe increase my omega naught up to maybe 10 million or a million, something like that, because it has to be very small. I can do that by making by reducing the size of the structure. You know, if I reduce the size of the structure, the stiffness starts increasing significantly. So I can do that. But then challenge becomes that how do I make sure that the signals are large enough so that they can be measured. Here we are assuming that I can measure any amount of voltage. It could be millivolts or microvolts or nanovolts, but my sensitivity also starts decaying very fast. So that is the challenge. And a lot of times what they do is that within the accelerometer itself or very close to the accelerometer, they have some amplifiers, charge amplifiers or some devices. So whatever is the signal which is being generated, it gets immediately amplified so that it can be measured reliably. Because otherwise, if that device, amplification device, is far from the location of measuring, it may get corrupted by the time it reaches the amplifier. So we mentioned about sensitivity, and so what we'll do is we'll define what is sensitivity. So for a microphone, we want a flat frequency response, which essentially means that for a large range of frequencies, the response curve is flat, you know, and we also want that it should be sensitive enough. If it has very low sensitivity and a very flat frequency response, it may still have limited use, because then it starts becoming difficult to measure the signals generated. So if you go to small microphones, very tiny small pressure type of microphones, they have very flat frequency response, but their sensitivity is very low. If you make the microphones large, because of this lambda over 2 pi factor, their frequency range becomes of a limited width, but their sensitivity goes up. So it's an interplay. My sensitivity, let's say S, is electrical output divided by mechanical input, which is your pressure in this case, right? There's a term called microphone sensitivity level, LS, microphone sensitivity level, and that is defined by this term, 10 logarithm in base 10 times, not times, I mean logarithm of E out over P divided by E ref. And I can make this 20 log E out over P, and I'll explain that how I made that jump. When the 2 became, once I remove 2, this becomes 20, but I also eliminated from here E ref. So E out is output voltage from the instrument. Okay, E ref is reference voltage. And typically it is 1 volt for, if my incident pressure is 1 microbar. 1 bar is 10 to the power of 5 pascals, which is 1 atmosphere. 1 microbar is 0.1 pascals. So E ref is reference voltage, and it's about like 1 volt for incident pressure of 1 microbar. So because of that, E ref goes away. And then P is RMS pressure. It is not peak pressure. RMS pressure on microphones in microbars. So it's not in pascals, but it is in microbars. From this relation, I get E out equals pressure times 10 to the power of Ls divided by 20. We also know that SPL, sound pressure level, is 20 logarithm of P divided by P ref. So which gives me P equals P ref times 10 to the power of SPL divided by 20. And my P ref, its industry standard, is 2 times 10 to the power of minus 5 pascals. So from this what we get is P, and I'll make it explicit in microbars, equals 2 times 10 to the power of minus 4 times 10 to the power of SPL over 20. And if I plug this back into the original equation,
5.
huh?
10 to the minus 5.
There's this 10 also.
P ref.
Yes, but then it also gets multiplied by 10.
So 10.
So it will be 20 microbar.
So 10, where will 10 come?
Hmm?
So 10 raised to the power SPL by 20 is there. No? It is not alone.
No. It is
It will be 20 microbar.
because we are doing in microbar, so because of there's a factor of 10, right? So that, because of that reason, it becomes 2 to the power 10 minus 4. Let's call that equation 2, and this is my equation 1. So from 1 and 2 what I get is E out equals 2 times 10 to the power of minus 4 times 10 SPL over 20 times 10 to the power of Ls over 20, or E out equals 0.0002 times 10 to the power of SPL plus Ls over 20 volts. And one thing I omitted earlier was that the unit of this is decibel voltage over microbar. They are not of the same decibel voltage over microbar. So we'll do an example. So let's consider microphone. So there's a microphone which has a sensitivity Ls of minus 50 decibel voltage for each microbar, and the question is that what will be the output of this microphone when my SPL is 85 dBs. So if SPL equals 85 decibels, what is E out? So I just essentially use this relation, E out equals 0.0002 times 10 to the power of SPL plus LS divided by 20, and what I get is 2 times 10 to the power of minus 4 times 10 to the power of 85 minus 50 divided by 20, and if I solve this I get 0.0112 volts. .2 millivolts.
SPL and LS are different units, so how can we subtract or write them?
But essentially what this process tells you is that you will know if you have some idea that your sound pressure level is going to be 120 dBs at the peak level and the minimum sound pressure level is going to be, let's say, 40 dBs, and if you want to measure it, you should be able to figure out what will be the output voltage from that, and when will my instrument be able to actually measure that voltage or not. That is what the
I
purpose.
suppose that LS has the same, LS has a unit decibel only, but it's just a V by mu bar is just a representation, because if we see the definition of LS, it's just a ratio, and ratio cannot have any unit. So it's V by mu bar just to tell that it's not there's an SPL or something like that.
Yes, but to his point is,
So if it is decibel, then there's no problem in subtracting.
that is true. So
So it has unit decibel.
So the answer to that question is, to your question is, E over E ref becomes non-dimensional, right? And P is in microbars, which is again a number. P again is in microbars.
ERF has also been defined for 1 microbar. So
Yes.
it's just a ratio for
Right.
1 microbar.
So it becomes a non-dimensional quantity. So a typical sensitivity for large microphones is something like half a microvolt for each microbar. You know what I mean? Or you can convert it into minus 125 decibels for each microbar. So that is on the low end, and then on the high end it goes up to 3 millivolts for each microbar. Other thing we'll now talk about is weighting. And, this relates to this stream of psychoacoustics. So let's say I am playing a particular instrument at a very high frequency, and I produce 100 dB SPL from that instrument. Now I use another instrument, let's say a bass guitar or a tabla, and it produces sound at 100 dB SPL, but it is at a lesser frequency. My ear, even though the SPL at different frequencies is the same, my ear will perceive the loudness of higher frequency as different from that which is coming from a lower frequency. This is how ear works. And this is so 40 hertz, 100 dB SPL will sound, will be perceived, it's not different, but will be perceived to have different loudness compared to, say, a 1 kilohertz compared to a 15 kilohertz, and so on and so forth. The other thing is that this difference in perception for different frequencies becomes more amplified if my overall sound loudness level is low. You understand what I'm saying? So if I'm playing the whole thing at, let's say, 85 dB SPL, different frequencies, then that difference in perception will be of much larger magnitude compared to if I'm playing the everything at higher dBs. So one perception is related to frequency band, and the other difference in perception is related to the overall loudness level. So this is how ear works. So in a lot of measurements which relate to human ear, if you are trying to reduce the overall noise in a big machine, machine shop where you are generating all sorts of frequencies, what people try to do is that they weight different frequencies by different numbers, so that the ear, based on whatever is the difference which is being perceived by the ear, because the aim is that the ear should perceive that, oh, the overall sound level has gone down, right? If you want to make it quiet, quiet means that ear is sensing that everything has become quieter. If you reduce the frequencies by the same amount, not the frequencies, by the amplitude by the same amount, the ear will not necessarily perceive that all frequencies have gone down by the same amount, because some frequencies it will perceive are still louder compared to others. So that is what relates to this idea of weighting.
So these weights cannot be, these weights will keep on changing with the SPL level.
And also loud SPL level, yes.
So how, there cannot be any standard. It can.
So that is what these three curves tell you. So you have this A weighting level is in blue. Okay. Then you have this yellow curve, which is B weight level, and then you have this C weighting level, which is in red. So A weighting curve basically is used for sound levels in general which are less than 55 decibels. Then your B is used for 55 to 85 dBs, and C is used for 85 dBs, in excess of 85 dBs. And there's also a D weighting level and a Z weighting level. Z is not shown here. We'll talk about that a little later. But it's important to know that in industry, when you measure sound, people say, oh, what type of weighting level you used? A, B, C. So you should be able to know what is being talked about. Now, the most prevalent weighting level in industry today is A. Most prevalent is A. Because as you see, in case of C, which is in red, it's pretty much flat across a very wide spectrum, from let's say 30-40 hertz to 5,000 hertz. It's pretty much flat. So A is the most widely practiced weighting level, and B also has fallen into disuse. It's used in very specific cases for some aircraft noise estimation. And these curves have been developed based on how ear perceives sound at different frequencies and at different levels. And based on that, on some statistical samples, people have developed these curves, and now they are the industry standard. And a lot of environmental agencies, say in India or in United States or in Europe, they actually enforce that if you're trying to solve noise-related problems, you have to weight your measurements based on some of these curves. So that is the purpose. You also see that there is this D weighting level which is in black, and what this is for is that if you have a bunch of, not a bunch, if you have a random noise where noise is at all frequencies, then the loudness perception of that random noise is different than the noise which is around 6 kilohertz. At 6 kilohertz, the loudness perception is at a higher level compared to random noise, which is a broadband noise. So that is why you have this peak at around 6 kilohertz. Otherwise, it's again more or less flat. I wanted you to get exposed to some of these curves, and you can also get charts for these curves could be translated into chart, the industry standard tables. You can use them and weight your sound pressure level measurements accordingly. Also, in a lot of sound systems, you may have seen this loudness control knob. Right? There's a loudness knob in some sound systems. It's not same as volume. Loudness, there's a knob, loudness, and that also it does the same thing. If you are playing it at a higher level, it uses some of these weighting curves to enhance certain frequencies and enhance not so much or not to the same extent some other frequencies. And if you play it at a lower level, then this loudness knob does something which relates to A weighting level.
The equalizers that is using.
Yes, something like that. So we'll come to the last portion. How do you add and subtract decibel levels? So if I have an 85 dB sound level coming from one speaker, and another source is generating 100 dB sound level SPL, what will be the overall SPL? Will it be 195? Huh?
Because it's logarithm.
So yeah, so you, because it's logarithm, you cannot just add them up. So we know that dB equals 10 log PI over Pref. Right. So PI over Pref equals 10 to the power of dB SPL over 10. So if I have a bunch of decibel sources, then total SPL I can write is 10 log summation of EI over Pref square equals 10 log So this is fairly straightforward, right? A question here could be, here what I am doing is I am basically using this 10 log relationship. But what I could also do is, I could remove this 2 and make this 20, right? Will that be an appropriate thing? Because I'll get a different number. Will that be right or will that not be, will that be incorrect? Which one? You'll only have one correct answer. So is this the right way to do it, or is that where you eliminate this power of 2 and put that into this 20, on the other side of the equation? Will that be the right approach, and why would that be the case?
You have defined dB in such a way.
But mathematically you can do this.
Yeah.
Mathematically you can do this. Decibel, if you remember in our original definition, is a ratio of energies. It's not ratio of pressures or ratio of velocities. It's ratio of energies, right, or power. And energy is directly proportional to V square or pressure square or displacement square of displacement, and so on and so forth. So I am basically, when I am adding decibels, I am adding up energies, total energy. I am not adding up pressures. So that is why eliminating power of the power number and putting it on the other side of the equation will be invalid, because that does not help me add energy levels. So we'll do an example. Let's say I have 3 sources, 96 dBs, 87 dB and 90 dB. P1, P2, P3. So what is the total SPL? So total SPL equals 10 log of 10 to the power of 96 over 10 plus 1087 over 10 plus 10 to the power of 90 over 10, and that gives me 97 dB. Gives me 97 dB. So it's just an increment of 1 dB. Similarly, if I have to do subtraction, then difference of dBs, 2 decibels, is 10 times logarithm of 10 to the power of SPL1 over 10 minus 10 to the power of SPL2 over 10. So suppose, so we'll do another example. Let's say we have a machine shop, a large machine shop, and there's some ambient noise, and then there's some also noise coming when a particular milling machine is running. So when we run the machine, then the total SPL level is, let's say, 93 dBs when machine runs. And when the machine is not running, let's say the total dB SPL is 85 dBs. Not running. So a logical question could be, what is the overall contribution of the machine, right, to the overall noise level? So SPL due to machine is 10 log 10 to the power of 93 over 10 minus 10 times 10 to the power of 85 over 10, and this gives me 92 dBs. So these are very, I mean, it does not become very apparent right away, and a very prompt answer would be what, 8 dBs, but the numbers are significantly different. Another example. So if I have, this is the most common usage, that you take a measurement in any experiment, its value is V1, then you take 4, 5, same type of measurement, V1, V2, V3. You want to be sure that the measurement is right? And these measurements will be different. Each time you do an experiment, the measurement will be different. So what is the average value? Now in linear systems, we just add V1 plus V2 plus V3, the entire thing divided by number of measurements. But here averaging requires a little bit different mathematical operations. So average SPL equals 10 to the power of log 1 over n, I equals 1 to n, 10 to the power of dB SPL over 10, ith value. So it's 10 to the power of 10 times logarithm of this entire expression. So another example I'll do is, let's say my 5 measurements are 96 dBs, 88 dBs, 94 dBs, 102 dB, 90 dB. Then my average SPL equals 10 to the power of log, or 10 times logarithm of 1 over 5, 10 to the power of 9.6 plus 10 to the power of 8.8 plus 10 to the power of 9.4 plus 10 to the power of 10.2 plus 10 to the power of 9, and that gives me 97 decibels. So each of these operations are important. They have practical usage. There are cases where you will be expected to subtract contribution of source A from source B. There will be cases where you will have to take averages. There will be still some other cases where you will have to add them up, and you have to be aware that when you are manipulating decibels, then the rules of the game are a little different. The last point I wanted to cover very briefly are two terms: correlated sound and uncorrelated sound. So a correlated sound is essentially when you have a bunch of sources and each source is generating sound, but you precisely know the phase relationships for each frequencies coming from all of these sources, and also at a specific time, if source 1 is generating F1, then source 2 is also generating F1 frequency, source 3 is also generating F1 frequency. So then then the sound coming from all these different sources, and the phase difference is also same, and also the phase difference due to the variation of location is also not significant. Then you can add up their pressures. In practical applications, most of the sources of sounds which we have, they are not correlated. So you run a machine here, a person is talking, a bird is chirping, there is no correlation between these two sounds. So you have a correlated sound, P total correlated is essentially P1 times T plus P2 times T plus P3 times T, and so on and so forth. A good example of this could be I have one speaker, I have another speaker, and both are having the same frequency response curves, and they are being fed from the same amplifier, the same signal, and also the distance between these two is not significantly large in context of the wavelengths which these speakers are generating. Then I can use this relation to add up the pressures. If I have uncorrelated sound, I could have one speaker, or actually a human being. So I could have 3 human beings. They are generating sound, they are talking, and the person who is listening is situated a little away. And in this case, E total uncorrelated equals E1, it's a square root of the squares of sums. So here we don't have any information on the phase. So again, while we are doing measurements, we have to understand, are we measuring correlated sources or are we measuring uncorrelated sources? And be aware, what is it that we are trying to do when we are summing up signals? That's all I wanted to cover for today. And thank you very much.